my screen. Can you see it in full mode?
Yeah, it's very good. So I'm going to give you a 10 minutes warning again.
Yes, okay, thank you very much. Today I would like to present some results from LCA of advanced lignocellulosic biofuels from the Biofuels project. The Biofuels project, funded under Horizon 2020, aims to develop innovative and sustainable value chains for producing advanced biofuels based on lignocellulosic biomass. One key aspect in Biofuels is to develop value chains which integrate the different key research activities of the project, namely cultivation, harvesting, logistic processes, and a process on slow pyrolysis, fast pyrolysis, and gasification processes. These value chains will be assessed within an integrated assessment as a combination of two approaches. The first approach is a consequential approach, which assesses potential environmental land use consequences regarding the large-scale uptake of the value chains. For instance, considering impacts on land use change, biodiversity, and so on. And if you're interested in results from the consequential approach, then I can recommend you the presentation of Fulvio Di Fulvio from EASA and his colleagues, and this reported presentation is available on the EU BCE platform. And the other approach is the attributional perspective, which focuses on process and product-related assessment for the individual processes, as well as the entire value chains. And from this approach, I would like to present you today the results. Yes, the assessment activities, the main objective of the assessment activities in Biofuels is to identify the most promising value chains. And this is based on two pillars. There we have the first pillar, the generic value chain assessment. This assessment is largely generic and will help to describe process and value chain specific benchmarking parameters like GHG emissions and costs. And on the other hand, we have a case study value chain assessment where we introduce regional characteristic, and these case studies are regionalized, plausible value chains with a clear regional reference for each of the process steps. And this assessment will complement the generic assessment to allow for detailed recommendations regarding the potential competitiveness of the value chains investigated in Biofuels. And here also the remark, if you're interested in this case study design, then I can recommend you the presentation of Björn Elbersen from Wageningen Research and colleagues, which is also available as a recorded session on the EU BCE platform. And today this presentation focus on the generic value chain, the attributional LCA of the generic value chains. The generic value chains, here a short overview about a short description of the generic value chain. We have considered 5 types of biomass. On the one hand, perennial crops, where we consider giant wheat and eucalyptus, one annual crop in form of sorghum, and we also considered agricultural and forestry residues. In order to produce a low ILOC advanced biofuels, that has been assumed that the cultivation is done on abandoned land. And then we considered 3 harvesting logistics for giant wheat and eucalyptus, which is resulting in different moisture contents. And we also considered different biomass supply chains. The first one is a direct supply from the field to the conversion site. And the second one is the integration of the slow pyrolysis. On the one hand, for drying the biomass, and on the other hand, to produce biochar, which we use in the gasification process due to the experimental work, referring to the presentation of Andrea, we do not consider biochar as a soil improver. Then we considered 2 thermochemical technology routes. The first one is the Milena gasification route. You can see this here in this value chain figure. And the second one is including an empyro site, fast pyrolysis plant for the production of FPBO with a subsequent gasification, and then the downstream processes for both routes, the Fischer-Tropsch synthesis and Fischer-Tropsch refinery. And today we will focus on the first technology route based on the Milena gasification and the subsequent Fischer-Tropsch synthesis and Fischer-Tropsch refinery. So much regarding the objective of Biofuel, the different approaches and the value chain design. Now I would like to turn on to the methodological approach, because we have considered different approaches. The first is according to the ISO 40/40, and the second one is more regulatory framework according to the RED II and the requirement that biofuels have to demonstrate GHG mitigation potential of at least 65% compared to a defined fossil fuel if they counted towards the national biofuel quota. There are some difference between the approval perspectives. In the first one, we have a lot of degrees of freedom, which allows us to have a dedicated, for instance, a dedicated consideration of byproducts. We have the Fischer-Tropsch refinery, a multi-output a process which produces Fischer-Tropsch diesel, Fischer-Tropsch gasoline, and Fischer-Tropsch kerosene as well. We will consider these byproducts by allocation according to lower heating value. And on the other hand, we have industrial process which produce a lot of surplus heat for external use, and we will consider this by substitution method. In contrast to this methodology, we have a more restrictive and simple approach regarding the method of the RED II, and there is only the possibility to consider byproducts also according to the lower heating value, but it's not possible to consider surplus heat. And I think later we see also the differences between the both approaches regarding the results. Let's come to the results. At first, I would start with the global warming potential of the value chains according to the ISO 40/40. We can see the emissions on the positive vertical axis associated with the production of the Fischer-Tropsch fuel, and in the negative or on the negative vertical axis, you can see the credits. On the one hand, given for improve of soil organic carbon by using abandoned land for cultivation processes. And the other one, this is the orange mark one, shows the credits given for replacing conventional district heating by the surplus heat from the industrial processes for external use. The balance from emissions and the credits is shown here as this little pink bar. And here we can see that there are several advantages by using the perennial crops, giant wheat and eucalyptus, especially compared to the emissions based for the value chains based on sorghum. There are a number of factors. On the one hand, there's a less demand of fertilizer, especially nitrogen fertilizer, and less emissions from the production of the fertilizer, and less emissions from field emissions due to the application of the nitrogen fertilizer. And on the other hand, we have some advantages regarding the improvement of the soil organic carbon. Here we have a higher credit for the carbon accumulation for the use of perennial crops or the cultivation of perennial crops than for the cultivation of the annual crops like sorghum. Regarding the value chains based on residues, you can see this here on the right side of the chart. This value chain assessment starts with the collection of the biomass. This means it's especially for straw that the cultivation processes, the upstream cultivation process, are not considered, but emissions from the compensatory fertilization and from baling processes. And these value chains do not benefit from soil organic carbon improvement. And since this fact, the overall emissions is a pink one bar, slightly higher than, for instance, the emissions from for the value chains based on perennial crops. In the field of the conversion emissions, you can see that the light blue marked emissions from the Milena gasification are responsible for the highest share on the overall emissions due to the used electricity and the electricity mix we assumed here with I think 30% of fossil fuels. If we compare the value chains with and without slow pyrolysis, the value chains with slow pyrolysis have an SP in the name of the value chain description. Here we can see that these are the yellow marked segment of the bar. They have additional emissions from expenditures and emissions from the use of natural gas and electricity. And despite these additional expenditures and emissions, the overall emissions are cause less, or the value chains cause in total less emissions than the value chains without slow pyrolysis. This is on the one hand due to the fact that biochar is used in the gasification, so we have a higher output in the Fischer-Tropsch refinery process, and on the other hand we have a surplus heat from the slow pyrolysis, and given also credit for slow pyrolysis heat and the heat from the Milena and Fischer-Tropsch production. So far to the global warming potential, let's have a look at the two other impact categories, the acidification potential and the eutrophication potential. We have set it in contrast to the GHG emissions, on the one hand to identify possible trade-offs, and on the other hand to compare it with the fossil diesel. And here you can see on the left side, on the left figure, the terrestrial acidification potential. The main driver here are sulfur dioxide emissions from, on the one hand, the use of fossil fuel, but also from the production of fertilizer and the use of diesel in the agricultural machinery, so that the value chains based on residues are more advantageous due to minor cultivation and harvesting processes, and the value chain based on sorghum due to the higher demand and application of fertilizer shows the highest emissions according to this impact category. But we can state here that the value chains are compared to a fossil diesel show a better performance. In contrast to that fact, freshwater eutrophication, you can see here also a strong cluster. The emissions values for the residue-based and perennial crops-based value chains are close to each other, but we have higher emissions from the value chains based on sorghum. These are the blue marked value chains. The emissions the eutrophication emissions are mainly driven by phosphorus and phosphate emissions on the one hand, also by using fossil fuels, but mainly by using phosphate emissions, and the sorghum value chains are here are causing here the highest emissions due to the higher demand on phosphate fertilizer. And here we have a trade-off in comparison to the fossil diesel, which has a much better performance regarding this impact category. And here we have a trade-off between the GHG mitigation and the eutrophication potential. The last results I would like to show you are here the assessment of the GHG mitigation potential according to the RED 2. And I've mentioned it before, and you have seen it, that the surplus heat and the credits for replacing the district heating have a strong influence of the overall assessment according to the ISO 40040. It's not allowed according to the method of the RED 2 methodology to consider the surplus heat by credits. And but nevertheless, all the considered value chains meet the requirements of a 65% GHG mitigation potential. What can we conclude from these results? Firstly, I've mentioned it before, the value chains based on perennial crops cultivated on abandoned land show are most promising from GHG perspective. Sorghum value chains are less competitive from GHG perspective due to the high amount or a higher amount of nitrogen fertilizer, optimization potential here in this field could be in the field of cultivation, harvesting operation by replacing maybe the fossil diesel. Straw and forest residues from GHG perspective are less competitive than perennial crops because they are not benefiting from the soil organic carbon improvement, but are competitive than more competitive than sorghum due to lower emissions from biomass supply. Forest residues have the best performance with regard to other impact categories like fossil depletion, I have not shown, and considering the time, eutrophication potential, acidification potential, and also the water depletion potential. Then the integration of the slow pyrolysis process for biomass drying and biochar production is advantageous. Depends a little bit on the moisture content, but this advantages for biomass with a higher moisture content, and yes, they show the lowest GHG emissions, and these are reached by using the biochar and the gasification. GHG emissions and the resulting GHG mitigation potential of Milena value chains could be improved by an increased share of renewable energy in the process energy mix. And the Biofuels value chains meet the GHG reduction targets required in the RED II, and thus expanding the portfolio of advanced fuels in Europe and meeting the GHG targets in the transport sector. And I think that is important against the background to meet the decarbonization targets of the Green Deal and the Fit for 55 package. Okay, I will close my presentation with this short overview about the partners in the Biofuels project, and here are some addresses where you can find some of the results.